And I guess you already know the basic gist of what is going on. Essentially, I'm currently fighting for my grade with pre-calculus now, not Algebra 2. I already graduated Algebra 2, and frankly, I got it with a passing grade of A- by the Asian standard. It's okay, I guess. So, currently, I am not doing so well in pre-calculus, and I have to find my math teachers to get my grades back, which is basically what happened. Pre-calculus is essentially Algebra 2 on steroids, and it's fundamentally hell for me. It's extremely stressful, and it's not giving me any good places to rest. Every single unit has some catch to it. That is extremely difficult for me, and all of them requires a lot of calculation. So it's essentially, as I said, it's Algebra 2 on steroids. There's no denying it, and I'm sure that I have to do better to actually get my grades back. So let's just start. So the first unit is the linear functions. We have went through this thing 3 times already, and I have to say, it's not gotten any easier. Here's the thing. So, I believe that you have already gone through Algebra 2, so you know the basic things about solving 3x3 functions, combination, elimination, and all the other methods. So I'm not going to run you through the linear functions again. But as you remember, with the linear function comes an incredible enemy that is called matrices. So, matrices in pre-calculus is basically the same thing that it was in Algebra 2. By that, you might think it has gotten a little bit easier, but actually it hasn't, because it's still the same thing. So, as you recall, matrices can do multiplication, addition, subtraction, and not division. We can only do that with inverse matrices. And the first 3 things are relatively simple. Addition, you can only add them with essentially the same dimensions. Subtraction is basically following the same rules as addition. It's basically adding the same column and the same row at the same position together. So you can only perform them if they are having the same dimensions. Multiplication, on the other hand, as you remember, is where things get complicated. So, multiplication is where things gets really, really, really complicated. So, you can do it with different dimensions, but you have to fit with a certain rule. Here's the first rule about multiplications, is that for a multiplication to remain the same, or to have the same operation, you must make sure that you're multiplying in the exact same order. If you're not doing it, the results might be kind of different. Like when, for example, in this just doesn't work. The results are completely off. As you remember, multiplication is when you take a row and then multiply it by a column. I'm not sure what is a row and what's a column, so you have to see the visual right here. So essentially, you take a row and you multiply it by a column, and then you add them together and you get your first answers. And then you do that for the second thing, and the third thing, and the fourth thing. We have done this already. We have done this in Algebra 2, and I'm not going to explain more about it. Another particular thing to know about multiplications is that it is essentially the most conflicting part about this entire thing, because this time multiplication is going to be really heavy on us, and it's essentially going to be really tricky to actually calculate some things. After we are done with basic multiplication, we go into basically the demon castle of the entire pre-calculus thing. The Cramer rules and inverse matrices. So, the first thing is that Cramer's rule remain essentially the same as we have done before in Algebra 2. Before we can go into Cramer's rule, we have to first figure out how to do determinants, or at least how to calculate determinants. The first thing that we have to know is how to calculate a 2x2 determinant, or the determinant of a 2x2 matrix. The first thing to do when you're calculating a 2x2 matrix is cross multiply. You multiply A with D and B with C. So you essentially get this, and you get AD to minus B and C. That's how you get a basic 2x2 determinant. However, this thing escalates when you're trying to do 3x3 determinants. 3x3 determinants are completely and utter nightmares. I am not happy with how I have to do this every single time when I'm trying to solve an equation. So to do the basic thing, you first take the first number of the first column, or just the first number, the most top one. And then you grab that number, isolate its row and column. By that you'll have a 2x2 determinant. We all know that already. Solve it, multiply it by the number you have isolated, and you got your first number, which is in positive form. The second thing is you have to minus the second number of the entire matrix, which is right. It should be the second row and the first column, as I remember row and column correctly. So essentially, you do the same thing that you have. Eliminate its row and column. You'll have a 2x2 determinant. Solve it. Multiply it by the number that you have isolated it, and subtract it from the equation that you have already got. The third thing goes back to positive form. So there's basically nothing that you shouldn't be familiar about this. This is very stressful, and it's very hard to do on a large scale, but you have went through Algebra 2, so I trust that you can handle it. At least you must handle it, or you'll die in this section. You must, essentially. So during that, you'll find the 3x3 determinant. Here's the complete equation, if I remember to put it right here. So that is 3x3 determinants. And things really escalate from the point on there. The first thing about Cramer's rule, you have to do the 3x3 determinant by 4 times. The first time you go and take the original thing, and then you turn the 3x3 equations thingy and turn that into essentially a matrix. A, B, C, D, E, F, G, it's all It turns into this. So the basic process of the Cramer's rule is to essentially take an equation and turn it into a matrix. I'm not going to do 2x2 matrices because it's essentially the same idea as a 3x3 one. So you take a matrix, you take an equation and turn that into a matrix. You just solve for its determinant, which will be the founding thing for every single other actions that you're going to do from now on. So after that, you replace the first column with the results of the equation, and then you plug that in there, and then you go there and solve for its determinant. Again, you have to do this for continued 2 more times for each root. You have to do it every time for each and every variable. It's stressful and it's hard, and I don't understand every single thing about it. The thing is that you're bound to make mistakes. So here's a general notion. Probably use other methods before you even attempt this. Try to use combination, elimination, any methods to double check this, because whenever I do this, there's a 10% chance I got things right the first try. And there's a 90% chance that I screw up in some small details in the small calculations. It's infuriating. It's extremely stressful when you're doing this in a test setting, and there's no way that you can do this perfectly when you're under stress. So after you got the determinant of the 3 variables, you divide them with the original determinant that you get, and that's essentially how you find the Cramer's rule. You basically solve for the 3 variables. I'm not going to do the 2x2 one because it's simply too easy, and you won't see that in 90% of everything we have covered so far.
Remember, we have learned everything that you have talked about throughout this entire 5 minutes. What's new about it? We got
Cramer's law. It is hard to enjoy every single thing because it is inverse functions or inverse matrices. We have learned that already, but you haven't seen its newest form. It's complicated. In case you haven't taken Algebra 2 yet, which you should have, here's a basic rundown of inverse functions. So inverse functions is essentially inverse matrices is essentially the opposite of a normal matrix. Every single matrices should have one, if I remember this correctly. And it's essentially the division of matrices. It can cancel out matrices in every single way, and it's a decently good way to solve for problems if you're using it for 2x2 equations. So we all know how to calculate 2x2 inverse matrices. You swap A and D and then make B and C negative. And then you got its determinant, or at least the determinant of the original function, and then plug it in there as a reciprocal, which is 1 over the determinant, and then the thing that you just rated, that is the opposite of a normal matrix. The real thing is, how do you do this for 3x3 matrices? The thing about 3x3 inverse matrices is that it has too many steps, and just as its determinant thing, you have to do this multiple times, and it doesn't really allow any chance of failure. It's hard! It's the only new thing is my kryptonite. This is essentially what matrices is. It's the end of me. So, how do you solve for the inverse matrix of a 3x3 function? As I mentioned, you first have to calculate its determinant because you have to plug it in front of the amalgamation that you'll eventually create. So do the determinant calculation, and then you'll get the thing. And then this is where things get really complicated. So the first step is to transpose it. Before you ask what transpose is, I'm going to explain it in detail. So transposing is essentially reversing its row and columns. So essentially, if the first row is 1, 2, 3, its first column becomes 1, 2, 3. You do that for the first row, second row, and the third row, and you'll get essentially a new matrix. And that's just the beginning. The second step is that you have to create an entirely new matrix. It's utter horseshit. There's no way around it. There's no way that you can do this with a peace of mind. So let's do this normally. So the first step that you have to do is like calculating the determinant. You take the first number of the first row, and then you destroy its row and column. You'll get a 2x2 to determinant, calculate it, and that will be your first number and your new determinant. And then you do that for the second number, isolate whatever number that is on the path, isolate its row and column, you'll get a 2x2 matrix, and then you can solve for it. So it goes for every other number. It's kind of like a roadmap. And this is relatively less stressful than doing the determinant calculation. And you only have to do the determinant calculation once. So I guess it's kind of less stressful, but anyways, it's still completely difficult to do. It's difficult to do. There's no way around it. After you repeat the process for the entire matrix, you have to multiply it by some checker tile thing, which goes in the pattern of... Wait a second, let me see my notes. So essentially, you'll have to multiply it by a pattern of positive, negative, positive, negative, positive, negative, positive, negative, positive. It's this. You have to multiply the entire pattern. You have to multiply your new matrix with this. You have to multiply the new matrix with this. Why? Here's the thing that I failed to mention. So when you're doing the making a new matrix thing, you have to use the transposed version of the matrix. So you can do this. This kind of mirrors the process of determinant calculation. So the first column, or is it the first avenue? I have no idea. So this thing will essentially mirror the things that you have done in the determinant calculation. So you can use it as a rule of thumb to see if you're right or wrong. And I'm still not done! I'm still not done with the thing, because you'll have to multiply the thing with the determinant. So here's the inverse matrix that you know. But to actually use the inverse matrix, we have to plug it within an equation. So this is the basic equation that you're going for. And then you multiply it with the same order as you do with the other side. You have to make sure that you multiply within the same order, or the answers of the both sides will not be equal, because that's how multiplication works in matrices. So you can cancel the things out and you get the answer. Except you still have to do this incredibly complicated multiplication method. So double check it like your life depends on it. It's hard, it's complicated, and it doesn't make sense. And that's the end of matrices. I have to say, after the second run, it isn't really that hard, but it's still really hard, and it will still be the end of me. Now, we have to move on to functions. So, functions basically remains the same that you have known it, but there are some kind of new things, such as piecewise functions, function operations, and also a new type of rational equations. So let's get started. A piecewise function is essentially an amalgamation of various different functions. Like you blend 3 different equations together to form a monstrosity that doesn't really work together. It may continue or it might not continue. Essentially, this is the most simple thing that you'll encounter in the entirety of pre-calculus. And it's going to be relatively simple. So, it can combine a quadratic function with a linear function, a rational function with a polynomial function, and any function with any functions. It's essentially a chimera of different functions. And it's fun. It's fine. There's basically nothing that you can do about it. It's relatively simple. There's not a lot of complication that arose to it, and it's basically all bound by a domain and things. So the x part will always state about the place where the function is supposed to be, and your job is to graph it. So you have to graph about 3 to 4 functions each and every time. But it's okay. It's better than matrices. Essentially, before you do any piecewise function, remember to remember every single way to graph any functions, because you'll be desperately needing it in any scenario that comes together. And here's an extra note. It doesn't have to follow a certain flow. It doesn't have to connect together. And it's alright. So we have to talk a little bit about discontinuity. Discontinuities is when things just doesn't add up together. Like, there's not an actual line that's coming together. So the first type of discountability is a jumping discountability, such as when things are completely separated from one another. Like when you have a function that's going here and it suddenly goes here. It's like jumping together, and it's essentially different. Now here's an important thing to note. It's different from the asymptotes, or as this chapter calls it, the infinity discountability, which sounds cool on the surface until you realize that it's just the asymptotes again. So why does it count as a discountability? Because whenever that line approaches, it goes either infinitely towards 0 or infinitely towards infinity. It's essentially a wall that blocks it, so the 2 points cannot meet together, so it becomes a wall that blocks the thing. So essentially, whatever is at that value cannot exist. This, of course, like the jump, creates discountabilities. Now, speaking of asymptotes, they're mostly caused by, undefined regions. And that's going to be quite common. And the other thing that's caused by undefined regions is a hole, or in this chapter it's called a removable discountability, or as you know it, every bank's favorite thing. It is basically a hole in the function that at that specific point doesn't work. It's mostly created when you're simplifying a function and you factor out a point that cannot possibly exist. So you graph the thing that you have already simplified onto, but that point on the original function still cannot exist. So at that specific point, there will be no values at that specific point, creating a hole, also known as a removable discountability. The next thing is operations with functions. Operation with functions come with a relatively simple premise. It is displayed in mostly with two D's, or are those called commas or are they called brackets? I'll just call them brackets. So they're starting with two brackets. One of them specify the type of operation that they are in, and the other one specify the variables that they're supposed to go inside of, which I'll just call it X for simplifying or explaining. So the first two basic types of these kind of operations is addition and subtraction. These two are basically the same. So when you're doing these, this will be denoted by these two things, and they will basically adding together f of x and g of x, which is the two functions I'm going to be assuming are together. And the second thing about subtraction is basically the same. It's f of x minus g of x. Now here's the thing, it's heavily result based, so you don't have to worry about graphing it so far. The second thing is multiplication, as everything should. It's multiplying the results of f of x and g of x. It's noted by f times g in the functions list, and then the x still exists, so it's multiplying f of x and g of x together. Again, it's heavily focused on results, so you don't have to worry about it so far. Now the third thing is division, which operates under the same premise. If you're going to graph it, it's essentially going to create an asymptote or some hole in the function, if you may. So this will essentially cause there to be a hole or a fracture in the thing. But you don't have to graph it, so it's again result based. So it's f of x divided by g of x. Now the thing that makes the entire thing quite interesting is when there is a hollow O in the FOG. So essentially it will kind of look like FOG, like fog. It means that the result of g of x becomes the new f of x. It's essentially that f of x is embedded inside g of x, or g of x is, there's no easy way to explain this. Let me think about it. After thinking about it, it's possible that it's just g of x becomes a new variable that goes into f of x. So it becomes f of g of x. So you throw the equation of, you put in, and use the function g to find the specific answer, and then you plug it into f of x. That's essentially it. That's all you have to know about function operations so far. Now the relatively new thing, or the same thing with an old premise, is polynomial graphs. It's still the same old polynomial graphs you know. So first factor it, try to get it as simple as possible, find its zeros, and then after you know it, you can just graph it, factoring by grouping, the other way of grouping. Anyway, I trust you because you have finished Algebra 2. If you haven't, please, again, get out of the video. So the new gimmick about graphing the things is that there's one very new thing called oblique asymptotes. So before we get into oblique asymptotes, let's get a basic gist of whatever graphing rational function was about. So essentially, when you're graphing rational function, there are two things that is the most important. The first thing is the vertical asymptotes. The second thing is the horizontal asymptotes. The vertical asymptotes are essentially the divider or the bottom parts of any rational function. They essentially separate the things because that thing separates, it's like a wall. Because when that thing equals to 0, You can't divide by 0, so you will have to find a way around it. So, rational equations, vertical asymptotes, act as a wall because you can't divide by 0, so whenever the x touches the zeros of the polynomial behind the divider, it basically becomes undefined and it will never reach the specific value of x. So that means that it creates a wall that goes infinitely positive or infinitely negative. So it essentially goes like this, and the thing will always follow the equation will always follow the vertical asymptotes, and there's no way of actually breaking them because they're cited within the domain. Horizontal asymptotes, on the other hand, is not defined specifically within the domain, so there is a chance of breaking through it. There are several conditions regarding how to graph a horizontal asymptote. So, here's a basic rundown. I'm going to refer to f of x as the top one and g of x as the bottom one. So, when the f of x equals to g of x, essentially what you're getting is whatever the first number or whatever the leading number is, it's basically that. Here's an example. It's clear that way. Let's move on to a second. So, when a g of x is essentially, the degree of g of x is essentially larger than the degree of f of x, you'll get, the asymptote would essentially be y equals to 0. It's a line. Every single asymptote is a line, and I'm always referring to degrees. Sorry for not making that clear. Now, the third thing is what is truly interesting. So, essentially, what the third thing is when the degree of f of x is larger than the degree of g of x. So, essentially, the f of x overpowers the g of x, locking the thing away. There is no horizontal asymptote when the degree of f of x is greater than the degree of g of x. Now, that is partially correct. But remember those things that I talked about ago? It turns out there is still asymptotes, but it's just not horizontal asymptotes. Enter oblique asymptote. It essentially exists when the denominator of the thing is greater than the degree of the denominator is larger by 1 than the denominator. So, that's when oblique asymptotes exist. Oblique asymptote is an equation on its own, but it's only a linear equation, so you don't have to worry too much about it. The problem with finding oblique asymptotes is that you have to be really, really diligent. So, to find oblique asymptotes, you have to perform long division, or whatever that is. So, when the numerator is larger than 1 learned by the denominator, you'll get the thing. Taking the example of that, essentially you'll have to perform long or symplectic division on whatever this is to find the line. So to get to this, you'll first have to work a little bit hard. By performing long division, you'll have to essentially divide the denominator by the denominator. And when you find that you cannot continue to divide, grab whatever that you got, or whatever you actually got, and then that will become your new oblique asymptote. That is your oblique asymptote as a slanted line. It works nearly the same as horizontal asymptotes. Lines can still break through it. It's basically quite similar to the things that we have done in Algebra 2. There's no getting around that. We're basically doing Algebra 2 on steroids. Why am I doing this? Remember that oblique asymptotes are essentially the same thing as horizontal asymptotes, and you still have to care for vertical asymptotes and beware of every single case-by-case standpoint because we're still dealing with rational function and they're completely illogical and hard to graph. Follow whatever asymptotes that the teacher has provided you, graph them, and hope for the best. That's essentially the entire process. of graphing rational function in this section. However, we're still not done with rational functions yet. At least, we're done with graphing it, but there's a new thing called rational inequalities, and it's essentially trying to find its negativity and positivity. There's also another new aspect in graphing these equations, is that you have to find its negativity. So here's the basic gist. It mostly maps around the central thing, which is also known as, the main vertical asymptotes. So whenever it approaches an asymptote, it draws like x goes towards the location of the asymptotes, and then you have to decide whether it goes positively. If it goes from the left, it goes from the negative. So you can say that, and then you cite if y goes to the positive infinity or the negative infinity. If it goes from the other side, it goes from the other side, you cite its positivity and negativity. You do this for every single asymptote, or every single vertical asymptote, and that's about everything about graphing. However, we're still not done with rational equation. We're only done with a part of rational equation. We don't have to graph it anymore. That's fortunate. But we're taking a look at rational inequalities. So rational inequalities is basically inequalities with rational equations and polynomials. It requires a bit more effort, and it is more of a pain in the ass than normal inequalities. There are two basic ways of doing this, and both of them works in given scenarios. So, the first way is the proper way, which requires for you to understand how this positivity and negativity works. That's essentially the end behavior of polynomials. So, let's take this equation for example. When it's larger than 0, it is asking for anything that is positive. So here's a basic illustration of how to do this. So essentially, let's start with a basic equation, such as x squared minus 1 times x plus 2. That works. So the parts where it changed is -1, 1, and 2. These 3 points are especially the places where the thing wagers. So you can first find out whether it goes to positive infinity or negative infinity at the tail end, and you can go up there. If it's not repeating, if it's not like a squared one, then you can just go through the zeros. It will go through like a wave pattern, and that's the first thing that you have to know. The second is essentially the same thing, except that it does a small trick. It follows the same step, identifies whatever points are the zeros, and those are points where it changed. However, here's the cheeky trick. You can plug in 1 or 0 to recognize whether if it's positive or not. This makes it a little bit easier to decide whether or not it's positive, because if it's not a squared thing, then it will essentially be positive, negative. It will still follow the same thing, but you don't have to specifically graph it. It's easier to do it that way, and there's no essential benefits for you to do the proper way. So just do it the little bit cheeky and faster way. So that's basically the way how to graph a polynomial inequality. But for rational inequalities, you'll find a very small problem that you can't really find. So, as you can see, the notation that I'm currently using is quite different from the notation that we're used to seeing. So, here's a basic rundown. When you're having like a small comma, like these small comma things, small encapsulated things, you're basically saying that it is not equal to, so it's greater or lesser, it's essentially the same thing. If you use a larger, what's the name again? If you use a larger bracket, you are basically saying that it is equal to that value. So whenever there's an equal sign, you have to consider whether or not that point is real or not, or if that point is actually or if that point is doing something. So you have to consider whether or not that point actually touches the thing, or does it fit the domain at all. And also, here's another thing: when the rational equation inevitably tails off towards an infinity, you can only approach infinity and you can never reach infinity. So you can only use the smaller brackets. I forgot what those things are. Don't judge me for that, please. Now here's the interesting part: the rational inequalities. You might think that it will be 10 times as hard, but the truth is it's basically the same as polynomial inequalities. But the catch is that you cannot equal to whatever is in the denominator, because if that number exists, the entire thing will basically go haywire and die. So you can convert any rational equation goes into a polynomial form like this, and it will work basically the same. Use the faster method to get the numbers quickly, and then follow the thing, note it quickly. Remember that you cannot equal to whatever number or the zero is on the denominator. And that's essentially everything that's to say about rational equations. You know the basic process of grouping functions, right? So partial fraction decomposition, which is sounding really cool, is reversing the notion and basically making that thing back to whatever original thing that we are ungrouped. There are two ways of doing this, and both of them are equally treacherous, and one is slightly faster. The normal partial fraction decomposition starts by giving you something like this. So if we're going for the long way, we'll have to first set the numbers of A and B. So basically, the process about partial fraction decomposition is to find whatever is the original form, as I just told you. So we can first set the original form as this, which will help us to find things more efficiently and more quickly. Partial fraction decomposition is to reverse the process of grouping. So essentially, you're going back to this form. So it will normally give you a completely grouped function, and that will be whatever you start with. And the first thing that they normally start you off with is, let's assume that the denominator has two variables. So you can set A and B as the original functions, or whatever values is on top of the original functions and on the denominators. So essentially, it will turn slowly into something like this, which you can slowly divide. Slowly you can turn it into like an equation where you can solve separately, or you can just deduct it normally. Because frankly, it is hard to explain this using pure words. And here is basically the essential process of how to do it. After you're doing it, you're setting up a function that is essentially what you're trying. Function that shows whatever that you're trying to get, and after you solve the function, you'll get whatever A and B originally is. And that's about it for the normal function. Now the second way of doing it is much faster. You first set up the thing as usual and then turn it into an equation or a set of equations. However, this time you can plug in 1 or whatever the zeros is in the circumstances, and then you can get it relatively quickly, and you can plug it in, and you can basically get the answer much more quickly than you anticipated or you would have if you just followed through it the normal way. Now the logical way is to just follow the faster way, right? Now, sometimes one works and the other doesn't, so I'm going to give you a basic example of when and how to use which methods. Now, note that partial fraction decomposition can only work when the denominator's degree is smaller than the denominator. So essentially, when the denominator is bigger, you have to perform long division. There are certain. Now back to what I was originally saying. So there are times where where one of the method doesn't work, and that method is when there are three denominators or more. In that cases you'll have to isolate each one of them, and they'll basically become all entangled together. So using the faster method, you can get rid of 2, but you cannot get rid of over 1. There is also another part that is very interesting. It's when one of the zeros is a squared zero, or something that has like the little 2 on top of it. When that thing is squared or cubed, the normal idea is to separate it into 3 different things, right? Well then, you're basically wrong, because when you're doing that, you're basically reverting it back to you're basically referring back into the normal things when there's no square zeros or whatever that's going for. So the logical way of doing it is to keep the square as a separate different thing. If you keep the square as separate different things, this again entangles the thing and makes the faster method doesn't work. However, you can still plug in the other numbers when it does work, and then you can slowly use the answer that you get to slowly get the things that you want. And that's partial fraction decomposition. That is the basic fundamental ideals of partial fraction decomposition. And I'm basically done with this section. So let's move on to the most problematic thing in this entire thing, outside of matrix, probability. It's going to be quite a doozy. Now, for the next section, we have to talk about probability. So, probability is essentially the most difficult in terms of how to memorize it and how to actually do this. Probability itself isn't that hard, but the problem is you actually have to think to solve the problems. You can't memorize a lot of the functions. You have to do this on a case-by-case standpoint and think about when or where to apply the functions based on your own knowledge. There's a lot of points of errors here, and just ask someone for help when you don't understand the concepts. So, the first thing on the probability checklist is counting. And there's no easy way to describe counting, as it is essentially the basis of all probability. It's basically counting the possible outcomes and multiplying them together. One of the first way of using this method, or how to do this, at least one of the first things that's introduced in this thing, is factorials, also known as the little exclamation mark that you would put on a very special sentence. So, the easiest way to explain a factorial is that it multiplies whatever. The easiest way to explain factorials is that it's an exclamation mark that you put behind a number. Now the exclamation mark denotes that you're multiplying it from 1 to all the way to the number that you're doing it on. So for example, 5 factorial, also known as 5 and an exclamation mark, denotes the multiplication from 1 to 5, which means 1 times 2 times 3 times 4 times 5. That is essentially the basis of factorial, and it works on every single thing. So that 6 factorial is multiplying from 1 to 6, and 1,000 factorial is multiplying from 1 to 1,000. And believe me, the number escalates very quickly, so you have to use a calculator if you're going to survive. And secondly, do not put 1,000 factorial. It will literally explode your calculator. Now, the primary use of factorials is to calculate the possibility of arranging something in the list. For example, let's take a look at the ways that you can list the words B, A, and D. Now, these 3 words are completely different things, so you can basically just say that it has the probability of 3 factorial, because originally there's 3 words that there's 3 letters that you can choose, and there's 2, and then there's 1. So it's 3 times 2 times 1. And that's basically all the way that you can arrange BAD. Now, if you're going to arrange the word water, which is 5 words, it's 5 factorial. Again, the numbers escalate very quickly. And now here is the final catch. However, when you're dealing with a list such as LOOK, you cannot just basically use 4 factorial because there's one very small catch. The O and O are exactly the same thing. So like OOLK and OOLK is essentially the same thing, and LOOK and LOOK is the same thing. So there will be like 2 possibilities that will be overlapping. So to solve that, you can just divide by 2. However, a more practical way that applies to every single thing is to divide it by whatever factorial that a repeat number have. So let's choose a fantastic word to actually display this. So for example, let's use the word fantastic because it's a fantastic word. So essentially, fantastic have multiple A's and 2 T's. So to do that, you'll have to divide whatever factorial that is in the word fantastic and divide it by 2 factorial and then divide it by another 2 factorials because there's repeating words between 2 and T. So that's basically the thing that you need to learn about factorials. This is going to be really useful when you're applying it in a list, and it goes beyond just words. Now spare me because I can't get into the nitty-gritties of the things that you have to do with counting and all the things, but essentially there's one prospect that you have to understand. It's all just a case-by-case basis, and nothing can help you. So you just have to remember the ways that you do this and then try to understand how it fits in every single thing. The second thing on our checklist is much more concrete and is much more explainable. So we're going to talk about the permutation and whatever the C thing is. So we're going to talk about So the thing about permutations is that it's a way of counting when sequence matters. The other thing, which is called combination, or whatever the C thing is different. So permutation is mostly denoted by 2 things. There's the P itself, and there's also the N and the R. The N lists the possible, all of the ways that you can, all the things that you can put something in the list, or all the possible outcomes, and the R is the things that you want to take out of the list. One of the ways that you can use this is to find a way to plug in something. For example, let's say that there's 2 items that you can plug. There are 4 spaces, and you have to choose 2 spaces to plug something in. So you have 4 outcomes, and you need to choose 2 of them. Essentially, that means that you can denote it by P42. That's the probability. Now, the function of permutation is actually quite simple. It is essentially n factorial, the total amount of outcomes that can happen, divided by n minus r factorial. That's the function of permutations. Its brother combinations, however, is quite different. First off, it completely ignores sequence. So ABBA and AABB is essentially the same thing. It is used for counting elections because your name doesn't matter. So whatever the outcome, when the number or when the things that are chosen are the same, they're essentially counted as the same outcome. So they're divided by an extra factorial, we're divided by an extra factorial, also known as r. Now, again, these 2 things may sound very simple, but I assure you, whenever you're trying to use them, you're trying to apply them to some sort of complex functions. So you're trying to do your very best. Everything in this section is a mix and match, and you have to do your best. The binomial theorem isn't hard. It's actually one of the most interesting parts about counting and probability. The binomial theorem is basically used to help you to find the number of terms and the number that is multiplied in a polynomial. For example, a plus b squared is a squared plus 2ab plus b squared. I trust you already know that, but none of us actually remember how to do a plus b cubed or to the power of 4. Something like that. The binomial theorem helps us identify it. Now the binomial theorem is essentially tied to the Pascal triangle. It looks like this, and it starts with patterns of 1 and it slowly branches down until you find the number of terms that you want. If you look closely, you can see that there are many similarities between the Pascal triangle and the binomial and the number of times that we multiply. This is basically how we find the number of terms in a large polynomial. So let's take a thing for example, like a plus b to the power of 4. Normally you won't be able to memorize it, but according to the Pascal triangle on the 4th line, you'll find it right there. It's simple, right? But you can't always draw the Pascal triangle. Because, you know, for example, if you're going to the 9th power, you have to go through the process of it 9 times. And it's going to be really, really hard to remember it. The Pascal triangle is essentially created by adding 2 different things together. So first, for example, on the second layer we have a 2 and 1. Adding them together will create a 3, and neighbor will also create a 3. And adding 1 and 1 together will create 2. It's essentially an never-ending loop that goes down and down forever. So there's a basic way of finding out whether or not, or finding out the number that is in front of the Pascal triangle. It basically goes something like this. It's shown right here. I'm not going to describe it because it's hard to describe it verbally. Essentially, after the second term, you're trying to do a combination thing that allows you to figure out how much is the values on a Pascal triangle. Now the way that most teachers would try to torture you with this is to ask you to find the numbers on a specific polynomial or a specific term on a specific polynomial. Now to do this, you'll have to do some engineering. For me, I list out all the possible, I'll first list out all of the possible terms and then solve it from there, but you might not be able to do that. And also there are some complications because occasionally, right, in the b term, there will be some negative powers. Again, this applies to every single polynomial ever created that is squared or to a power of something. There will be many ways of teachers trying to torture you with this, and you have to. Here's a specific equation for finding the Pascal triangle. It's going to be hard for you. And I trust that you can do this. And we're done with the warm-up. Now we have to do the actual hard parts of the probability section. The probability section, all the things before, those are counting. Those do not exist as probability. Those are the ways that you can find probability, but frankly, that counts as counting, okay? Here's the basic probability idea. So P of A equals to the outcomes that you want and the total number of possible outcomes. It will come up a lot, but we'll ignore it for now. Now the fact is that there's many different types of probability, and this is only one of them, which is called a theoretical probability. Experimental probability, on the other hand, refers to the probability that you're actually throwing a coin, and it's going to be really close to this number, but it doesn't really fit it. The first probability that we're going to talk about is the independent event, or a probability where 2 events are independent of one another. Let's take probability of rolling 2 dice. The possibility of those dice interfering with each other is 0. So whenever you throw a dice, they're independent of one another, and they're essentially not going to connect. So let's take the rolling the dice example here. So let's first take a look at the notations, because most of them are triangle notations and I forgot them most of the time. So here's a quick recap. The upside down U refers when things intersect. For example, let's take these two circles here, and the intersecting part, the middle part, is the part that we're looking for. So A upside down B, it refers to that part. And A larger U B refers to the entire thing or the entire list. So all this is included. So let's assume that we're talking about the two dice examples here. So when we throw a dice and another one, they're independent of one another. So when two events are independent of one another, the possibility of the middle part essentially equates to possibility of A times the possibility of 2. So let's say that the possibility of getting a 1 and then a 2 essentially equates the possibility of getting a 1, which is 1 out of 6, times another 1 out of 6. Again, I'm just generalizing here, and there are many ways that teachers can come up with creative solutions to make your lives miserable. So go online and find some things that help you. Now, an extension of independent events is when an event is given. For example, me rolling a dice with 3 given that I already roll a dice of 2. The equation of calculating any given events is P as a possibility of an event that is happening with the other event, also known as PA upside down UB, dividing by the actual probability of PB. Now for independent events, because P intersecting B is essentially PA times B, so the possibility of something that is given happening is essentially P of A. This will be used to test if something is independent of another or not. It's going to be a really simple question, and this thing is going to be really complicated when we get to the harder questions. So we're done with basically the independent events. Now there are two things. Now there is the other kind of probability where two things are essentially mutually exclusive. An example of mutually exclusive events is flipping a coin. So when you flip a coin, there are only 2 possible outcomes, and those 2 outcomes cannot happen together. For example, when you flip and you get a head or a tail, you essentially means that a head cannot happen with a tail because that wouldn't make sense, would it? There's only one possible outcome. So when these 2 events are not happening together or cannot happen together at the same time, that means that these 2 events are mutually exclusive, such as me punching you in the face and me becoming friends with you. It's mutually exclusive. Those things cannot happen together in any given circumstances. Now, thanks to this, our life will be much more simple when we're calculating the probability of everything together. So, possibility of everything together normally goes by mostly goes by the likes of A plus B and then minusing probability of A, plusing the probability of B, and then minusing the intersecting part because that place will overlap. Now, since there's no overlap, so that means the whole set essentially equates to possibility of A plus possibility of B. Makes our lives a heck of a lot easier, and it makes me happier. So here is where things get complicated. We're going to talk about poker. You know, the game, or specifically a way to play poker. So this game, also known as Texan Poker, I think it's called Texan Poker, I'm not sure, I'm not a gambler. So, you're picking 5 cards from a deck of 13 times 4 cards. So that essentially means that your total possibility is, the total way of things happening is going to be P 13 times 4, choosing 5 cards. And from there, a lot of things can happen. Let's first take a look at the possibility of a pair. So a pair is when two cards are the same. So when two cards are the same, we will first have to determine which of the values are the same. So when a pair happens, we'll have to first discover which value it is. So choosing outstanding values, we'll choose one value, also known as P. So basically, we're choosing certain cards out of one because we're finding one specific value. So after we find the specific value, also known as C13 picking one, we're basically going to find the colors that you're going to be using. The possibility of that is C4 choosing 2. So that's a way that we find basically a pair. However, we still have to account for the other cards. So we'll have to multiply the thing by the rest of the 12 cards. So essentially there are 12 cards left, and there are 12 cards that are available for value, and we will have to pick 3 out of the values, and then we have to multiply it by whatever color, which is known as 4 cubed, I think. Now here's the thing that I forgot to mention. So essentially 4 cubed is choosing 4 3 times. This is when things that are happening can repeat. So for example, when things can repeat, it's essentially 4 times 4 times 4. The second thing that we're going to explore is 3 of a kind. 3 of a kind is essentially a pair but with 3 cards. So you're having 3 cards of the same value but different colors. So essentially you'll have to choose one value out of the 13 cards, which we're going to assume that it's some random card. That we'll have to check which of the 4 colors that we choose. So picking 3 colors out of 4 possible options, and then we do the rest of the things that we have done already. So there will be 2 cards left over. So just picking 2 cards out of the remaining 12 possible values, and then multiplying them by 4 each time. 4 of a kind is essentially the same thing. So you'll have to pick one value out of the possible 13, and then you'll have to multiply it by choosing 4 colors out of the 4 possible options, C4 picking out of 4. And then essentially from there on, you have one possible cards left. So you pick one value out of the remaining 13 cards, and then you multiply it by 4, which is the 4 possible colors that you can have. Now there's no other way of doing things because there's only 4 colors, so there's no 5 of a kind. And essentially that's the basic things. However, there are more terminologies such as flush, royal straight flush, and other things. So let's go through them one by one. So a royal straight flush refers to something that is happening at the same time. So first, a royal flush means the largest possible flush that can be. A flush is essentially a continuous of 5 cards, like 1, 2, 3, 4, and 5. That's a flush. And for a royal flush, it's starting from... So, a royal straight flush refers to when 3 things are happening to once. So, the first thing that happens is that it is a flush. A flush is a set of hands that is essentially having the same color, or is in the same suite. For example, 5 cards of the same color is called a flush. The other thing is that it is a straight. There are 10 different types of straights in the entire game. And there's not 13 straights because of a very specific reason. You cannot start a straight using K, J, or whatever. You cannot use those things. So essentially, we're limited to 10 straights. And royal straight flush is very special because it is a royal flush. The royal flush is the last flush, and it is the highest point scorer in the game. And it's a straight flush, which means that there is only 4 different ways that you can get a royal straight flush. So essentially, Royal Straight Flush is one of a kind. So the possibility of getting a Royal Straight Flush is 4 divided by C52 picking 5 cards. As for flush and straight flushes, I'm not going to get into the probability of that because it's all easily inferable and it's going to be really difficult when you're trying to deal with these terminologies. Now we're finally at the end of everything. Binomial distribution, that's the end of everything. So binomial distribution contains very specific rules to make this work. So to make binomial distribution work, each trial must be independent of one another. The other thing is that each and everything must be mutually exclusive and there must be only 2 outcomes. So these are the 3 rules that is basically defining whatever is going on here. So this is the equation for binomial distribution. It works on several different principles. So the first combinations and is essentially the numbers of trials that is happening. So for example, let's assume that we have 5 trials and that there is 2 successes. So we're choosing out of the 5 trials, we're picking 2. And by the way, because it's combinations, because the exact order doesn't really matter, such as winning 2 games from winning the first game and winning the second game, and winning the third game and winning the fourth game is essentially the same thing. They are both winning 2 games. So essentially that's why we're using combination. So the second thing on the equation is the probability of success. We're bringing that to the total number of times we have succeeded. So essentially that means that we're taking the probability that we actually win to the power of whatever. So the last thing in this entire thing is basically the probability of us losing. So, as I just said, we have a 40% chance of winning, so we have a 60% chance of losing. Taking that to the power of how many times we fail, which is the total number of trials minus the total number of successes, which is evident by the equation right here. So this basically shows how many times we have failed so far. And that's binomial distribution. Binomial distribution is particularly used to measure the possibility of us winning something a number of times, such as me flipping coins 5 times and getting heads 3 of the times. It's very specific and is used to calculate the times that we win in a specific event where 2 things are mutually exclusive. And that's the end. I have no more things to talk about, and I'm finally free, assuming that I don't have pre-calculus with the final test. I'm going to work my essay now, and none of you can stop me. I have finished everything. Woo!